Hi, this is an example problem from Chapter 20. Pause for a moment and read the question. So in this problem we have a simple circuit where we have a resistor, 150 ohms, connected to a 5-volt battery. What that 5-volt means, this is the diagrammatic symbol for a battery. This is the symbol for a resistor. And the voltage 5 volts across the battery means that there's an electric potential difference as charges go through the battery. They can gain electric potential energy, and then that can be transmitted by those charges to other parts of the circuit, in this case the resistor. So we think of this as like the low side of the battery, 0 volts, the high side, 5 volts, and the difference between it, delta V, is 5 volts. However, in this chapter, instead of writing delta V, we're going to go ahead and just say the voltage of the battery, the electric potential difference. We're just going to call it V for simplicity. In Chapter 20, they do that. Let's look at Part A. Part A asks, what is the current in the circuit? We're going to use Ohm's law to calculate this. Now, there's no decrease in the electric potential along the connecting wires. So this 5 volts here, it's also going to be 5 volts at the edge of the resistor. The 0 volts here, it's going to be the same all the way through the wire, and so all the way back to the other edge of the resistor, 0 volts. So we have a voltage across the resistor, and we can relate the current through the resistor, which is also through the battery, using Ohm's law. Ohm's law, the way I usually write it to remember it, is just V equals I R. But if we actually solve for the current here, it gives us a better idea of what Ohm's law means. So I is equal to the voltage across the resistor provided by the battery divided by the resistance. And so V, the voltage, that's what drives the charge to flow from a high to low potential energy. R, on the other hand, in the denominator, that impedes the flow of charge. It's the resistance of the resistor. And you can think of that as these charges that are flowing from high to low in the resistor. They're going to encounter ions fixed in place throughout the resistor. They're going to crash into them, collide with them, and they're going to be losing energy as that occurs. And that's going to impede the flow of current. So to calculate the current in this case, the voltage is 5 volts. And the resistance here is 150 ohms. Now at this point it's important to be in SI units, so volts, ohms are the SI units, and we're going to get a value here. This comes out to 3.3 times 10 to the minus second. Amps are the units that we should be getting in this case. Now there's a lot of new units sometimes in these chapters, electricity, magnetism, so you want to be sure that you know what are the SI units for each of these. This is an omega. And that way you'll get your answers in the right units. Let's double check real quick to see if this makes sense. So we've got a volt divided by an ohm. It turns out that an ohm, if we look at Ohm's law, it's equal to a volt per amp. That means we're going to multiply by the reciprocal here. And we do indeed get amps as we expected. All right, let's look at Part B. The power dissipated in the resistor. We need to calculate that. The power dissipated by a resistor, or power in a circuit in general, is just given by I, V times I, the voltage times the current. And this makes sense because the voltage is, another way to think about it is joules per coulomb. And the current, an amp is a coulomb per second. And so this is going to give us the rate of power in the circuit, joules per second. Let's go ahead and put our numbers in here. So 5 volts multiplied by 3.3 times 10 to the minus second amps. And we're going to get a power here of 0.17 joules per second. Another set of units we can use as a watt. A watt is a joule per second. And so this all makes sense to us here. Let's look at part C. How much energy is delivered from the battery to the resistor in 1 minute? So the idea here is that charges have potential energy in the battery, and they want to flow through the circuit to decrease that potential energy. The charges will carry the energy from the battery and will deposit it in the resistor, and the form of the energy, essentially it's converted from electric potential energy to heat in the resistor as it heats up. Now, in reality, it's electrons that are flowing to carry the charge. And electrons actually go from low to high, so they go this way. But look at the currents actually going the other direction. That's because we used the wrong type of current, just because that was set up a long time ago. So what we say instead is that instead of negative electrons flowing and carrying the energy, which is transmitted to the resistor, we just say that instead it's positive charges that flow from high to low, and they carry energy from the battery and transfer it to the resistor. How much energy is delivered to the battery to the resistor in 1 minute? Well, we remember that power, joules per second, right? And using this idea, we can go ahead and figure out what the energy delivered is. So energy, I'm going to write it as delta PE because it all comes from a stored electric potential energy in the battery. That's going to be the power multiplied by the time interval. Because power is joules per second and time is seconds, it'll tell us the total energy that has been transferred. Our power, 0.17 watts, multiplied by the time. 1 minute is 60 seconds. In fact, it's better, instead of using watts, why don't we use joules per second here? We can cancel out our joules, and we're going to get an answer equal to 10 joules. That is the energy that was transferred from the battery to the resistor, dissipated as heat in the resistor, and it was carried by the charges. All right, let's look at part D. How much charge flows through both the battery and resistor in 1 minute? Well, the current in this circuit here is a steady current, which means it's a constant rate of flow, in this case going clockwise, and so same amount of charge flows through everywhere, the battery, the resistor, the wires, in the same time. How much charge is it? Well, one way to do it is to go back and think of the definition of current. Current, I, it's the amount of charge that passes through the circuit in a certain amount of time. Using this equation, we can solve for Q, and that's going to be equal to the current, the rate of charge flow, multiplied by the amount of time that passes. In this case, we've got 3.3 times 10 to the minus second amps, multiplied by 60 seconds. And in this case, instead of amps, why don't we use an amp is a coulomb per second, and so we're going to go ahead and cancel these guys out. We'll get coulombs, the quantity of charge, and putting that in the calculator, we get a value of 2.0 coulombs of charge. Now I want to just show you one other way to do part D here, an equivalent way. So we remember from chapter 19 that the change in potential energy is equal to the charge multiplied by delta V. I just use absolute values for everything here. And if we can use this equation to go ahead and calculate the value of charge. Assuming everything here is positive, absolute values, I'm going to drop them now. But we can just go ahead and say Q is equal to the amount of energy divided by the voltage, the electric potential difference divided by the battery. In that case, we have 10 joules divided by the voltage is 5 joules per coulomb. I'll use those units. We'll cancel out our joules, and 1 divided by coulombs becomes coulombs, and so again we get the exact same answer. Just another way to look at that.